here we're just getting an overview of our different classes of functions, starting with linear and absolute value. So our linear functions have mx plus b form, or if we use point slope form, it could look like this. It looks a little different with function notation, but maybe you're used to seeing y minus y1 equals m times x minus x1, where we have this coordinate x1, y1 provided, as well as this slope. Now, our slope can be interpreted many different ways with function notations. We would have this difference in outputs over difference in inputs. Using function notation, you could also think of it as x and y's if you had two coordinates. Or change in y over change in x is another way to think about it. So let's just go through quickly and kind of look at what we can get from these different equations, or forming the equation based on slope, y-intercept, and some specific points on the graph. So this right here is our point slope form. Sorry, with our first one. Let's start with the first one. That would make sense. 3 minus 2x. So our slope would be this -2, because that's what's multiplying with x. And then our y-intercept would be 3, which would be our value of b. So in terms of slope, we would just copy over that -2. For the y-intercept, we would have the coordinate 0, +3. So our y-intercept is always 0, b. Our slope is our value for m. And then a specific point on the graph. In this case, what we would do is just choose some x value, plug it in to get the y coordinate. So like this one, use -3. So we would just go 3 minus -3 times 2, which would be a 3 plus 6, which is 9. All right, for this form, our slope is right here. And what we're also getting out is an x and y coordinate. Now keep in mind that we expect to have subtraction, so you'd want to think of this as minus a -1/2. So this would be our y coordinate, and this would be our x coordinate. So for slope, I would just use a +1/2. For our y-intercept, I don't know yet, so I'll find that in a second. For a specific coordinate on the graph, what we can grab is when x is 1, y is -1/2. Now to get our y-intercept, there's a few different ways to go about this. We could change this to slope-intercept form. You could also just plug in x equals 0. So what that would look like is we're looking for f of 0. We know we're adding 1/2 there, equals 1/2 times 0 minus 1, which would be a +1/2 equals -1/2. Subtract 1/2 from both sides. So f of 0 is equal to -1/2 minus 1/2, which is a -1. So our y-intercept would be the coordinate 0, -1. Okay, this one we're given slope and y-intercept. So I would just go, it's going y equals, but let's use our function notation. F of x equals 2/3 times x plus 4/3. For a specific point on the graph, all I would do is plug in a value. How about x equals 1? The only one you don't want to use here is 0, because that's already been found with the y-intercept. So that'd be 2/3 plus 4/3, which is 6/3, which is 2. Okay, this one gives a slope and a point. So with this, we could go f of x minus, and our y coordinate is 0, equals, our slope is -1 times x minus 5. And actually, this would be pretty fast to change to y-intercept form, or sorry, slope-intercept form if we wanted to, because that -0 just disappears. And then if we distribute the -1, that would be a -x plus 5. So I'm seeing a y-intercept of +5. So we have the coordinate 0, +5. Okay, when the slope is 0, we're graphing a horizontal line. So we'd be graphing something like this, where our line is just y equals a number. So our function is equal to whatever that number is, And what we can do is find that number based on the coordinate that's given to us, where they say we're going through y equals -1. So that means our function is equal to -1 everywhere, which means our y-intercept is 0, -1, because that y coordinate's going to stay the same throughout. Absolute value functions look like this. So the absolute value turns values positive, so we can plug in negative numbers. It's just the output's always going to be positive. So with this, our domain in terms of x values is all real numbers. So -infinity to infinity, but the range is going to depend on which direction are we going in and where is that point occurring. So in this case, with our basic form of the function, it starts at y equals 0 and we include 0, and then it's going off to positive infinity. Something we could notice is that it's made up of two lines. Like we have y equals -x on this left-hand side, and then y equals +x on this right-hand side. And we could write that as a piecewise function, which we'll talk about more in another review video. But we could rewrite this as this is the function -x for when x is less than 0, and it's +x when x is more than or equal to 0. But let's just get some more practice with those graph transformations here and how we would move that around. So again, we're going to start with our horizontal and vertical compressions. This one is just going to have a vertical compression by 1/2. And then after that, we'll move left 1, right 2. What I'm going to do is start with the kind of the, it's not really a vertex, but the turning, let's call it the turning point. So with that, it's not going to move with vertical compressions, but it's going to move with the horizontal and vertical shifts. But with this compression, nothing happening there yet. And then we would usually be at 1, 1, but now we'll be at 1/2, or we'd be at 2, 2, now we'd be at 2, 1. So just all those distances got cut in half. And what's really happening is our slope changed. Instead of a slope of 1, we now have a slope of 1/2 occurring. So there's our vertical compression by 1/2. And now I'm going to move left 1, right, up 2, not right 2. That would be silly to keep moving horizontally. Okay, left 1, up 2. And then we have our slopes of 1/2, so we could just follow that there. And then we would just use a ruler or straight edge to draw our nice straight lines, and it would go on forever like that. Okay, another scenario here. Again, if we have something multiplying with x inside, we need to factor it out. So I'm going to factor out a 2, so we have an x plus 3. So I'm seeing here is, okay, we're going to reflect over x, and vertical stretch by 2, horizontal compression by 1/2. And at the very end of everything, then we're going to move everything left by 3. Okay, so in terms of that turning point, that isn't going to be affected here. So that reflection, the vertical stretch, horizontal compression, that's going to stay a point there. But let's see what happens to what we had was 1, 1 before. So now it's going to reflect down here, and then we're going to stretch it downward by 2, and then horizontally by 1/2. And then we'll have the same on the other side. And then let's just follow 2, 2. It would reflect, stretch out by 2, compress by 1/2. And then with that, we have our slope. We can see a slope of -4 there, and it would just continue on. So I could grab more points just by following that slope of -4, and then +4 on the other side. Okay, from there, we're going to move left by 3. Let's see, 1, 2, 3. And then my slopes of 4 are preserved. Oops, 1 over. And then we can draw our straight lines. Straight-ish lines. I should use a ruler, but we're all good there. So, little graph transformations that we can use with our absolute value functions.